The gentle murmur of deep water against fine sand drifts over you now, a sound softer than breath in the stillness of the night. You can almost smell the brine and the distant, low scent of minerals warmed by the subterranean heat, a deep, comforting musk carried on the slow tide. Feel the rhythmic sway of your own breathing, mirroring the eternal, patient ebb and flow of the unseen currents below, drawing you deep into a state of tranquil suspension. Chapter 1: The Ancient Dream and Continental Hypothesis. Focus: Preplate tectonics models, early evidence, Pangaea concept and timescales. Slowly, we begin our drift back through the colossal measures of time, sinking into an era when the geography of our world was a far stranger, more intertwined tapestry. We are speaking of deep time, of millions upon millions of years, where the concept of movement was merely a subtle, almost imperceptible side deep within the planet's mantle. Before the definitive framework of plate tectonics crystallized, the initial seeds of wonder were sown by pioneering thinkers, individuals whose meticulous observation challenged the rigid assumption of a fixed Earth. One must travel back to Alfred Wegener, a name that echoes softly across the annals of geological inquiry, who proposed, with profound intuition, a monumental rearrangement. His hypothesis, gently unfolding, suggested that the continents were not fixed entities, but rather colossal rafts that had once been joined together in a magnificent, singular supercontinent. He envisioned a landmass so immense, so perfectly fused, that its very name became the epical concept of Pangaea. The sheer scale of this idea, of a life cycle for the entire global geography, was staggering. Pangaea, approximately 335 to 200 million years ago, represented an ultimate unity, a single breathing organism of rock and life, spread across a uniform, integrated lithosphere. Imagine the profound connection. The Appalachian Mountains of North America sharing a common lineage with the mountain ranges found in the Scottish Isles, an ancient, undeniable resonance passing across vast, now separated oceans. Wegener's evidence was a compelling mosaic of multiple disparate fields of science. We consider the fossil records, noticing the distribution of certain plant and animal life forms, the Glossopteris asterisk flora, for example, which appeared in remarkable geographic isolation. Yet the fossil pattern suggested a single, contiguous landmass was required for their original dispersion. Another pillar of his argument rested upon the geological matching, where distinctive rock types and mountain chains appeared to continue seamlessly, yet were separated by thousands of kilometers of deep, blue-tinged water. And then there was the subtle, rhythmic curve of ancient coastlines. When examining the fit of the continental margins, particularly the remarkable jigsaw fit between the eastern coast of South America and the western coast of Africa, the fit suggests not merely coincidence, but a profound and methodical puzzle piece arrangement. These margins acted as silent witnesses to a once united existence, carrying the etchings of a forgotten shoreline. The implications of Pangaea were not merely geographical. They spoke to the very mechanics of life and climate. Such a unified supercontinent would have generated utterly different deep ocean current patterns, affecting global weather systems in a manner entirely distinct from the patterns we observe today. The planet's climate would have operated under a slower, more powerful engine of transition, a vast, slow sigh of geological patience. For decades, this idea remained a hypothesis, beautiful in its logic but frustratingly unproven by the most accepted physical models of the time. Scientists were initially skeptical, viewing the sheer magnitude of the continental movement as mathematically impossible under the known forces of physics. Yet, the deep geology, the accumulating evidence of time and erosion, insisted upon a more dynamic, profoundly interconnected Earth. Chapter 2. The deepening blueprint and mid-ocean ridges. Focus, evidence beyond continental fit, seafloor spreading mechanism, paleomagnetism. The monumental breakthrough that transformed the hypothesis into established science arrived with the advent of sophisticated technology, allowing us to finally look beneath the surface, into the silent, submerged heart of the planet. The true blueprint of continental movement was etched not on the continental shelves, but in the depths of the world's oceans, particularly along the massive, sprawling features known as mid-ocean ridges. These mid-ocean ridges are vast, submerged mountain ranges, stretching across the majority of the globe's ocean basin, forming continuous chains that delineate the boundaries where the plates of the Earth are most actively separating. They are colossal geological seams, running continuously for tens of thousands of kilometers, silent monuments to the energy released at the planet's structural joints. The most vital evidence gathered in this investigation concerned the mechanics of seafloor spreading. This concept elegantly explained how the vast supercontinent had disassembled itself. Instead of the continents pushing against each other solely, the oceans themselves were actively growing, forming new crust material at these central, underwater mountain chains, and pushing the older crust away in opposite directions. The magma, rising quietly from the mantle beneath the ridge crest, undergoes a slow, cool process of crystallization, solidifying into new basaltic rock. This process is measured with incredible precision. The rate of crust generation at these spreading centers is consistently found to be between 2 and 5 centimeters per year. To place this rate in gentle perspective, it is only slightly faster than the growth rate of a fingernail. Yet over millions of years, this seemingly minute rate results in the separation of entire continental masses, reshaping the globe fundamentally. The confirmation of this steady, rhythmic spreading mechanism was the profound realization derived from paleomagnetism. Earth's magnetic field, much like any giant dynamo, is not constant. It periodically reverses its polarity. When the initial magma solidifies at the ridge crest, it traps a signature of the magnetic field present at that precise moment in time. This signature acts as an immutable chronological marker. Mapping these magnetic stripes across the ocean floor revealed a stunning, perfect symmetry. On either side of the mid-ocean ridge, parallel to the spreading axis, alternating bands of normal polarity and reversed polarity are recorded in the oceanic crust. These magnetic stripes, striped like lines on a massive, submerged ledger, represent periodic pulses of magnetic field reversals. This symmetrical pattern is the physical proof of the spreading, As magma forms and moves outward from the ridge, it carries the current magnetic signature, depositing a band of rock, and then repeats the process, creating a mirror image of magnetic history on both flanks. This established, rhythmic twin pattern stands as the indisputable physical signature of a planet that is eternally, slowly, rebuilding its ocean floor. Chapter 3: The Engine of Movement and Plate Dynamics. Focus, mantle convection, driving forces, classification of boundaries, plate interaction. If the oceanic crust is the perfect evidence of the spreading plates, then the mechanism driving that spread, the engine itself, resides deep within the planet's viscous, semi-molten mantle. We must consider the enormous, slow-moving processes of mantle convection, the planetary circulation system that provides the underlying motive force for the entire spectacle. The Earth's mantle behaves like a highly viscous, incredibly hot fluid over geological time. Heat generated by the decay of radioactive elements deep within the core slowly drives colossal, circulating currents within the planet's deepest layers. These rising and sinking currents are analogous to slow, majestic currents within a body of water, a planetary conveyor belt of unimaginable scale. As hot, less dense material rises from the deep mantle and eventually cools, it spreads laterally beneath the overlying lithospheric plates, generating the colossal stresses necessary to power continental movement. These plate movements are not merely drifting. They are riding upon and interacting with the inertia of these deep, churning convection currents. We classify the interactions at the plate boundaries according to three dominant, yet contrasting physical interactions: divergence, convergence, and transform movement. Understanding these boundaries allows us to study the complete mechanical cycle of global geology. At divergent boundaries, the spreading mid-ocean ridges, the plates are pulling apart gently, letting the rising magma fill the widening gap, which we have seen documented by the magnetic striping. This process is fundamentally one of creation, of new, relatively cool crust being steadily laid down. In stark contrast are the convergent boundaries, where the monumental action unfolds. Here, the plates are colliding, often with massive, crushing force. When one type of plate meets another, the resulting interaction dictates the magnitude of seismic and volcanic activity. We must differentiate between the types of collision with utmost care, for each scenario produces a unique geological signature. The critical distinction lies in the types of crust involved. Oceanic crust, which is rich in dense basaltic rock and constantly being recycled, and continental crust, which is thicker, less dense, comprised primarily of granitic material, and is more buoyant. The interaction between these two different materials forms the basis of some of Earth's most spectacular and sometimes most dangerous geological events. Finally, there are the transform boundaries, where plates slide horizontally past each other in a magnificent shearing dance. These movements, such as those observed along the San Andreas fault system, generate tremendous frictional stress, releasing it periodically in form of powerful, jolting earthquakes. They represent a lateral sliding, a non-crust generating, non-crust consuming motion. Chapter 4, the embrace of collision, subduction zones. Focus, oceanic continental collision, Wadati Benioff zones, deep mantle recycling, geological forces of compression. The most transformative interactions, in terms of shear force and deep planetary exchange, occur at the convergent boundaries, specifically in the zone known as subduction. This process is fundamentally the great recycling mechanism of our planet's lithosphere, ensuring that no crust is ever truly permanent. When an oceanic plate converges with any other plate, whether it be another oceanic plate or buoyant continental crust, the inherent difference in density governs the outcome. The denser plate, overwhelmingly the oceanic plate, is inevitably forced to descend back into the Earth's mantle, a process of dramatic, silent descent into the hot, deep depths. This downward plunge is guided by gravity and is measurable in deep geological markers called the Wadati Benioff zones. These zones trace the path of the descending slab of rock, dipping steeply and often extending hundreds of kilometers deep into the mantle, acting like a massive, submerged, planetary fault line. As the oceanic slab descends, it does not descend in isolation. It carries with it immense amounts of water, the trapped sediment and materials that were once part of its source. This trapped water is key because as the slab sinks into the progressively hotter and greater pressures of the mantle, the water is released. This released water acts as a profoundly powerful flux, a chemical catalyst that drastically lowers the melting point of the overlying mantle material. Essentially, the water lowers the critical temperature threshold, allowing the mantle rock to melt and generate magma. This newly formed magma, being lighter than the surrounding rock, then rises, sometimes breaching the surface to form chains of magnificent, sometimes volatile, volcanoes, the characteristic arc volcanoes of subduction zones. For instance, traversing the Pacific Basin, we see this mechanism repeatedly. The Pacific Plate subducting beneath the North and South American plates, responsible for the formation of the Cascade Range and the Andean Mountain Belt. Here, the relentless, immense pressure and the chemical interaction of water with silicates create the conditions necessary for the periodic, slow building of mountain ranges. This cyclical collision and sinking represent the planet's attempt to achieve a state of dynamic equilibrium. Magic is generated, mountain ranges are built, and then, over tens of millions of years, they are consumed and recycled back into the Earth's deep storage, leading to the steady, majestic march of global plate boundaries. Chapter 5, Continental Collision and the Building of Mountain Ranges. Focus, continent-continent collision, lack of subduction, crustal thickening, specific examples like Himalayas. When the oceanic element is removed from the equation and two continental plates collide, the geological outcome is profoundly different, representing perhaps the most majestic collision documented by Earth's history. This is the scenario of pure continental versus continental convergence. Because continental crust is characterized by its low density and high buoyancy, neither massive landmass is willing or able to surrender to the deep embrace of the mantle. The result, therefore, is not subduction, but an unprecedented and unimaginable process of massive crustal thickening, of sheer compression that refuses to yield. The continental crust behaves less like a single, uniform sheet and more like a series of intensely folded, wrinkled layers. As the immense compressive forces converge, the rock layers buckle, crumple, and stack upon one another in an enormous, protracted act of geological resistance. This process generates the world's highest and most formidable mountain ranges. The grandest and most paradigmatic example of this collision is the formation of the Himalaya Mountains. This monumental range is the physical manifestation of the continuing, slow-motion collision between the Indian Plate and the Eurasian Plate. When the Indian continental plate, which was once a separate tropical landmass, slowly collided with the Eurasian supercontinent, the immense kinetic energy and compressive strength caused the crustal material to crumple, fold, and pile up. Instead of one plate sliding entirely underneath the other, the force built up until the least resistant material began to buckle upward, creating the immense peaks of the Himalayas. Pause. To visualize this, imagine a slow, inexorable, and continuous force pushing two vast continental crusts together over millions of years. The resulting geological tapestry is one of tremendous stress and incredible uplift. Pause. Other major continental collisions, such as the one that formed the Appalachian Mountains, show the same principle. The immense, overwhelming force of colliding crusts building mountains of unimaginable scale. Pause. This process highlights the sheer, undeniable power of plate tectonics, the continuous recycling and collision of continental masses, building and reshaping the planet's surface on timescales we struggle to fully comprehend. This is Earth's ultimate monumental construction project. Pause. 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 pause, 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 Pause. 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 Hash summary of geological processes and tectonic theory. This document provides a detailed overview of the fundamental concepts of plate tectonics, the theory that describes the large-scale movements of Earth's lithosphere. It synthesizes knowledge from various geological periods, explaining how continental drift evolved into a comprehensive global model. The theory of continental drift, Alfred Wegener. The premise started with Alfred Wegener's continental drift hypothesis which proposed that the continents were once joined in a single supercontinent called Pangaea, meaning all lands. Over time, this supercontinent fragmented into the landmasses we know today. Wegener amassed compelling evidence supporting this idea, including 1. The jigsaw fit, the remarkably complementary shape of the continental coastlines, particularly South America and Africa. 2. Fossil correlation, identical fossil records, e.g., Glossopteris flora and Mesosaurus fauna, were found on landmasses currently separated by vast oceans, suggesting they once occupied the same climate ecosystem. 3. Rock type and mountain correlation, matching mountain ranges and rock strata of the same age were found on opposite sides of oceans, e.g., Appalachians and ranges in Scotland. 4. Paleoclimate evidence, evidence of ancient polar ice deposits, tillites, existed in tropical regions, indicating drastic past shifts in global climate. The initial flaw, the missing mechanism, while Wegener's evidence was powerful, his initial proposal lacked a plausible mechanism. He was unable to explain how continents could plow through the solid oceanic crust. The modern model plate tectonics. The concept of plate tectonics revolutionized geology by providing both the correct framework and the physical engine for continental movement. Key components: lithosphere, the rigid outermost shell of the Earth, composed of the crust and the rigid uppermost mantle. This lithosphere is broken into massive, moving plates. Asthenosphere, the semi-molten ductile layer beneath the lithosphere upon which the plates float and move. Convection currents, the driving force. Heat escaping from the Earth's core causes the mantle material, asthenosphere, to circulate in slow, powerful convective currents, dragging the overlying tectonic plates along like rafts on circulating fluid. Types of plate boundaries, zones of interaction. The movement of plates is not random. Major geological events occur at the boundaries where plates interact. 3 primary types of boundaries exist. 1. Convergent boundaries, plates colliding. Where 2 plates move toward each other, tremendous energy is released. The outcome depends on the combination of crust types, oceanic versus continental. Oceanic-continental convergence. Asterisk, the denser oceanic plate subducts, sinks, beneath the lighter continental plate. Result, asterisk, deep ocean trenches. Intense seismic activity and volcanic mountain ranges, e.g., the Andes Mountains. Oceanic-oceanic convergence. Asterisk, the older, colder, and thus denser oceanic plate subducts beneath the younger one. Result, asterisk, deep ocean trenches and chains of asterisk volcanic island arcs, e.g., the Mariana Trench and associated islands. Continental convergence. Asterisk, neither plate is dense enough to subduct fully. The crust buckles and folds upwards. Result, asterisk, the formation of massive, non-volcanic mountain ranges, e.g., the collision creating the Himalayan mountains, where Indian plate collided with the Eurasian plate. #2. Divergent boundaries, plates separating. Where two plates move asterisk away from each other. Mechanism. Asterisk, magma from the mantle rises to fill the void, cooling and solidifying to create new crustal material. Result, asterisk, the formation of asterisk mid-ocean ridges under the ocean and continental rift valleys on land, precursors to new oceans like the Great Rift Valley in Africa. This process is essentially seafloor spreading. #3. Transform boundaries, plates sliding past. Where two plates slide asterisk horizontally past one another. Mechanism. Asterisk, crust is neither created nor destroyed. The interaction is characterized by intense friction. Result, asterisk, major transform faults asterisk, which are zones of severe, shallow earthquakes, e.g., the San Andreas Fault in California. #/ conclusion. Plate tectonics successfully integrated Wegener's historical observations with the mechanics of mantle convection and plate interactions. It established a unified, dynamic model of Earth science, explaining the global distribution of earthquakes, volcanoes, mountain belts, and the evolution of the planet's supercontinents. The Earth's surface is not static. It is a slowly moving, recycling system driven by internal heat.